We have discussed in the past the need and the use of right triangle trigonometry. The implications being that if I want to get from one point to another point, we could go directly, or we could go by components. This forms a right triangle, and if we are given an angle, we can use ratios like sine and cosine to help us find those components. We've done so in the past with Newton's laws. Taking note that when we did a problem like this, we broke it up into components. So there was a y component, for example, and then there would be an x component, and we would set those up according to the axis that they pertain to. In our discussion of kinematics, we did discuss horizontal kinematics, so objects moving left and right in an x-axis direction. And we talked about free fall kinematics, which was strictly on a y-axis direction, up and down. One of the key things about free fall kinematics is the use of gravity as a type of acceleration. But what about those cases where it's neither left and right or up and down, but it happens to be both left and right and up and down? So when you throw a ball, when an object is shot, it doesn't go on forever. At some point it makes its curvature and it hits the ground. Notice that it fell a height, delta y, but it also traveled a distance, delta x. And so what we need to do at this point is that there's a need for two-dimensional kinematics being built upon the foundation of free fall and horizontal kinematics, using those at the same time, but doing separately by breaking it into components like we did for Newton's laws. So if we have an object going through a parabolic trajectory in the air, and let's say it's at this point right here, we know it's going like this. However, if we were to break that up into an x and a y component, we could say that it's going this far, x-axis, and we can say that's going this far in this direction. And I shouldn't say far, my apologies, that the velocity vector component is of that magnitude. So this is Vy. And that's superimposing at that point in that trajectory an x and y axis coordinate system. And so what we see is that we can pretty much ignore that orange velocity vector and just work with these components. And so what I'm proposing is that we take every object that's going through an angle trajectory. So we'll say that it's launched at an angle theta. And that in the process of going through that parabolic trajectory, that there's an x component of the velocity and there's a y component of the velocity. Now, what's interesting is to see how those change and how they depend on certain aspects. So let's look at a simulation and observe the velocity vectors and the components of those velocity vectors. So again, when I'm talking about components, I'm talking about an x component and a y component. And right now, I just want us to look at the velocity. So let's go ahead and fire this, and I'm going to go ahead and step it so we can see it in action. Oh, psych. Okay. Oh. Okay, let me step it this time. Okay, so here is a cannonball coming out of the cannon, and you're noticing that there's some components here. And I want us to focus on the y component, the Vy. So that means I'm looking at the up and down arrow. Right now it's going up. But as I step this bit by bit, and again, we're just focusing on this green arrow that's going up. What do you notice about that green arrow that's going up? Only the one that's going up. Notice that it's getting smaller. Notice that at the apex, it's gone. we say that the apex is the point at which the object hits the highest point in the trajectory, and so that's the apex. Notice that on the way up from here to here, that the velocity, the vertical component of the velocity, was actually pointing up. But at the apex, it was equal to 0. What do we expect for the vertical component of velocity on the way down? Let's go ahead and step this. It changes direction, and it's getting bigger. And if the velocity is increasing, that means it's accelerating. And again, we're looking only at the y-axis. So on the way back down, Vy was pointing down. We can use fancier words for this, right? So on the way up, the vertical component of the velocity, we notice that that velocity vector was decreasing, which means that the object was decelerating. It was slowing down as far as the vertical component is concerned. At the apex, the vertical velocity was equal to 0. And on the way back down, the vertical velocity was increasing. And therefore, it was accelerating. So on the way up, it was decelerating. When it got to the top, the acceleration, the velocity was 0. The acceleration didn't necessarily change. It was the velocity that changed. And then on the way back down, the velocity began increasing, and so it's accelerating at that point until it hits the ground. Yeah. So that should remind you of free fall, right? Because with free fall, we shot a rocket up or whatever we threw up in the air. What was responsible? Let's step this up. What was responsible for slowing it down? And what was responsible? Here's the apex. You can see that it's 0 right there. And then what's responsible for bringing it back down? Okay, you get the picture. Gravity. Okay, gravity is responsible for slowing it down on the way up. Gravity is responsible for spinning it up on the way down. The question becomes, well, here's a trick question, right? What is, if the gravity is slowing it down on the way up, right? Same thing here. And if gravity is responsible for making it accelerate on the way back down, then what is responsible for making the velocity, the vertical component of velocity, equal to 0 at the apex? It's gravity. Okay? So throughout this whole trajectory, the gravity never stopped. The acceleration never stopped. The acceleration was affecting the velocity. And so we saw that. Now, the gravity only works on the y-axis. And so our focus on the vertical component of velocity on the y-axis must be affected by gravity because gravity is on the y-axis. Let's look at the x-axis component. So this is the green arrow that is going to the right. And the question is, how is that green arrow going to the right changing? Is it getting smaller? Is it getting larger? What happens when we hit the apex? We're looking only at, and again, we're only looking at the green arrow that's pointing to the right. This is the Vx. This is the Vx x-axis component. We've already discussed the Vy. This is the Vy component, which we're not focusing on right now. We're focusing on the Vx component. So, what happens to the size of that Vx component, of that green arrow going to the right? How does it change? How is it affected by this whole thing? It doesn't seem to be affected. And just to be sure and clear, let me take off air resistance. My bad. let's make sure we reset this and not have any air resistance. Okay. Velocity vectors, components, cool beans. Alright, let's do that. I'm just gonna get rid of this thing. Okay. So I'm gonna fire this thing. Oh, snap. Oh. Dang. Okay. So if I go ahead and fire this thing, fire. Okay, and just to prove it to you, okay, here it is, fresh off of the cannon, and I'm looking at right here and right here. How long is this green one? 5.63 meters, something like that. 5.65. Okay, great. So I'm gonna leave the measuring tape there, and you know what? Let me move it over here just for kicks at the apex, and let's see if when this cannonball gets there, if it's the same length. Okay, let's test this out. And again, we're focusing on the x-axis. Oh snap! It's the same length. Well, maybe over here. Let's try over here. Okay. I'm gonna get arthritis from all this clicking. Okay. Oh snap! Where is it? Okay. It chopped my thingy. When I moved it over here, it made it shorter. See that? So that's the simulation's fault. But it's the same length still. Okay, so what we're noticing is that unlike the y-axis component, which keeps changing, the x-axis component stays the same. Oh, that's fun. So let's watch this in slow motion. Keep an eye on those components. Notice the y became 0, and now it's going to increase and accelerate downward, but the x-axis component stays the same. Now, you're wondering, why, Mr. Rover? Why does the x component not change? Doesn't gravity affect it? Gravity works on the y-axis only. Gravity works downward. The horizontal component of velocity is on the x-axis, is moving to the right. So, to answer your question, no, gravity does not affect the horizontal component of the velocity vector. It does, however, affect the vertical component. So gravity affects it, but the x-axis, it does not. Now, if we do have a velocity vector, right, v, and if there's a component, an x component, vx, and there is a y component, vy, which we typically don't put it there, right? We typically put it over here like they did in the simulation. But recognize that because of the geometric properties of vectors, I could go ahead and translate this over, and it'll be the same vector. So I can go ahead and translate it over here, and that will allow us to recognize that this is a right triangle. And how can I relate all of these together? Well, by the Pythagorean theorem. So that's how they're all related. And if you start asking yourself, well, Mr. Rover, isn't it true that gravity affects velocity? Yes. If you're talking about this velocity, v. Why? Because v, if we want to square root this and actually get the value for v, we have the Pythagorean theorem. And if the y value is being affected by gravity, then this total answer is going to be affected by gravity, and therefore the velocity ultimately will be affected by gravity. But what we're making a claim here is that the horizontal component is not affected by gravity. I think I've said the same thing many times. I just want to make sure that you're aware of how this works. So there is the overall big picture of velocity, which we just summarized with the Pythagorean theorem, and it's made up of two components. The velocity vector is made of two components. The horizontal component, which is not affected by gravity, and the vertical component, which is affected by gravity. And it will change. It'll decelerate and accelerate, and so that'll change the values of that vertical component. When would the horizontal component change? Well, it would change if we have something like Iron Man, right? And he's coasting along, and all of a sudden he decides to turn on whatever he turns on. then he could change his horizontal component. But as far as we're concerned, AP Physics 1, we don't do that kind of stuff. We're not Iron Man, all right? We're still stuck in the cave. So what we should be concerned about is recognizing that the horizontal component does not change and remains constant. It remains constant. And the vertical component, it does change. And once you recognize on how to separate these things, then it is as simple as just pick the right kinematic from back in the day, right? If I'm using a horizontal kinematic, then use a horizontal kinematic. If you're using a free fall kinematic, then you're using the vertical components that go with it.